Hi, everyone. Sorry I couldn't be here for this Monday, but I am going on the senior excursion to Knott's Berry Farm. I know it's after the AP test and none of you are particularly excited to keep learning chemistry, but this is the first in a very short series of lectures where I just give you a little bit of information and a little bit of practice with things that I wish I had had practice on before entering college level chemistry. So in this one, we're going to be talking about organic chemistry line diagrams, which we actually have talked about a little bit this year, and also functional groups, which I didn't really touch on very extensively. So first here is examples of organic molecules and structures that you might see in an organic chemistry class. So we've got testosterone here in the middle, ampicillin, caffeine, and a whole lot of things that really just they're kind of par for the course for any sort of organic chem class. One thing that I'd like to point out is the difference in one of these structures. So if we look at sucrose, this one right here, you'll notice that this structure looks just slightly different than the other ones. And that's because this structure as a whole represents more of the orientation and real shape of this particular molecule. So you'll notice that some of the lines are thicker and some of them are thinner, and it looks to be kind of drawn in 3D. So this is representative of some of the more advanced structures that you might be looking at. But you see elements of that in some of the other structures as well, like this one right here. And here you're seeing wedged lines versus dashed lines. And all of that is utilized to represent the 3D nature of these molecules. Now, there is another difference that I'm going to point out, and that's the difference between this sort of wedged dashed line and this one. So this dashed line up here represents a real bond. So you'll see that kind of wedge shape like this, versus this dashed line down here that's just quite literally a dotted line. That is not a full bond. That's not a full covalent bond. This instead would be an association like potentially a hydrogen bond. All right, moving on to structural formulas. You have seen structural formulas before. We went over this at the very, very beginning of the year when we were talking about nomenclature of certain organic compounds. So going through the different ways you could see molecules represented, we have our full Lewis dot structure, which is not something we've done a whole lot with in chemistry, but you can represent bonds with just dots of electrons next to one another. So this is the molecule ethanol, which would be C2H1234560, or you could represent it C2H5OH. There's a couple of different ways you could write it out. So that would be the full Lewis dot structure. The way you're most used to seeing it, though, would be this way right here. That would be a Lewis dot structure with your covalent bonds represented as lines, or a Lewis structure for short. Sometimes you've seen molecules represented more like these down here, and this is when the covalent bonds are actually omitted from the structure, but the formula is written out kind of structurally. So it's split up into its different main groupings. So you see this CH3, which would be the analog to this right here. You see in the middle, there's the CH2, which in the Lewis structure you see right there. And then finally our OH over there. So rather than writing that formula as C2H6O, which doesn't really give you an idea of how any of that is bonded together, a lot of times, especially in organic chem, they'll show you a formula like this that gives you a better idea of the overall structure. And then we have this situation here, which is very, very similar, except they're including our free electron pairs on the oxygen. But I would say that this one you don't tend to see a lot. It's more often that one. And then finally, we have the line diagrams, which I introduced to you at the beginning of the year, where our hydrogen atoms are implied and our carbon-carbon bonds are shown by a line. So we would have one carbon here, one carbon there, and then our hydrogens would be stacked on and implied. Just like that. So down below, I have a little bit of rules for line diagrams. Each solid line represents a 2-electron covalent bond. If you see a double line like this, that would be a double bond. A triple line would be a triple bond. When no atom is drawn at the intersection of 2 covalent bonds, it's assumed to be a carbon atom. So whenever you see lines that look like this, each point here is assumed to be a carbon atom. However, if you see something like that, this point right here does not have a carbon atom bonded to an oxygen. This is just a bond to an oxygen. So the closest carbon would be there. All non-carbon atoms must be drawn with any hydrogens attached to them. So you would never see this with some implied hydrogens next to that N. If there are hydrogens there, you would see them in the formula. Because if you saw this, there are no hydrogens attached to that. Because again, unless those hydrogens happen to be attached to a carbon, they must be written in. Lone pairs are often omitted in these types of formulas, but sometimes you'll see them included. So you might see something like that, or you might see something like this, but quite often it's not pictured because they are assumed to be there. So our example of a more complex structure would be capsaicin, that chemical that gives peppers their spiciness. If I were to draw out the full Lewis structure, it would look like this. But that is very, very messy and very, very cumbersome to draw. So instead, organic chemists will abridge that structure and imply all of those carbons and most of the hydrogens, and you'll get a much cleaner looking structure like that. But if you take a second and you look at this, these structures mean the same thing. The same amount of atoms are present. But I do want to draw your attention to this section right here that has an analog right there. A lot of times you will see things like this where they kind of do an abridged structural formula on one end that actually represents a much more complex series of bonds. So just pay attention when you see things like this, that it can have a particular shape, and I'll point that out as we go. When we start factoring in molecular shape, so talking about VSEPR and how certain atoms are oriented in space, there's a couple of things. If you see a regular line like that, that represents a bond that lies in the plane that is the same as your paper. If you see a wedged dashed line like this, that means that that bond is pointing down to behind the paper. So it's going away from you. And then this represents a bond that is coming towards you. It's directed in the plane in front of your paper. So it's just a little way to represent 3D structure of a molecule. So our sample problem here asks you to draw a full Lewis structure with covalent bonds represented with lines of cyclopentanol, as well as the associated line diagram of cyclopentanol. So my note for you is that the prefix cyclo means the molecule is cyclic or circular-ish. In this case, since it's pentanol, cyclopentanol, it's going to be shaped like a pentagon. So all of those carbons are connected to one another. The suffix OL means that there is an OH group on that ring, and we'll look at some of those suffixes and what they mean in a little bit. So if you'd like to try this on your own, go ahead and pause the video. And then if you have no idea what to do, keep on, bear with me. So we're going to start out with 5 carbons. And I know that there should be 5 carbons because of this pent in the middle of that word, pent referring to 5. So the first thing that I'm going to do, since I know that it should be circular-ish, is bond all of these carbons together in a pentagon shape. The next thing that I'm going to do is pay attention to this OL suffix. Now, as the note says, that suffix means that there's an OH group on that ring. Now, it doesn't give me any more information than pentanol, cyclopentanol. So if there were more than one OH group, that name would tell me. And there are ways to figure that out. I'm not going to go over nomenclature too heavily in detail right now, but I'm just going to go ahead and bond that OH to a random carbon. Because again, it's not specific as to which carbon that's bonded to. So I'm just going to pick one. The next thing that I'm going to look at is this A right here. And if you recall way back at the beginning of the year, we did talk about nomenclature just a little bit. That A means that there are no double bonds anywhere. If it had been an E, that would mean there was a double bond. If there was a Y, that would mean a triple bond, but there's not that. So there's no double bonds between any of these carbons, which means that this structure is what we call saturated with hydrogens. So what we need to do is we need to fill the octets of all of our carbons with hydrogen. So looking around, every carbon except the one here that I picked to bond that hydroxide to has 2 bonds attached to it, except for this one, which has 3. So I'm going to complete that carbon's octet by adding a hydrogen here. I'm going to add 2 hydrogens to every single other carbon. And again, I'm doing that because we are assuming that all of these octets are complete because we are not told that there is a charge anywhere on that molecule. So this would be the full, complete Lewis structure of that. But again, that was really annoying and really cumbersome to draw. It would be much easier to draw the line diagram. So just draw a quick pentagon and throw an OH group on there. And so that would be the same molecule represented 2 different ways. Moving on to functional groups, the thing that I have not really talked about before. Functional groups are something that they don't tend to spend a whole lot of time on in organic chemistry in college, but they do expect you to be able to recognize them on command, which is kind of annoying, especially when you are scrambling to memorize a bunch of things. So I have included a lot of different things here, and I'm not expecting you to memorize any of these right now. This is quite literally just a reference and a little bit of practice for you going forward. Functional groups are important because they represent groups of atoms that have particular physical and chemical properties that can determine overall reactivity of molecules, and you can use them predictively to do electron pushing with reaction mechanisms as you get higher in chemistry. So our first table lists our hydrocarbons. We have alkanes, alkenes, and alkynes. These 3 we did talk about at the beginning of the year. So an alkane would be a hydrocarbon that does not have any double bonds in it. So this over here would be an example of an alkane. An alkene, let me draw that same thing, might be something like this that does have a double bond or more than one double bond potentially. An alkyne would be something like this, which has a triple bond in the middle of it. So again, we have talked about these. We looked at those in the beginning of the year. So over here on this side, we have some examples of alkanes, alkenes, and alkynes. So on the top here, we have an alkane represented in, again, that abridged structural formula. In the middle, the alkene here is represented by a line diagram. And again, we have an abridged structural formula there. But you could make a line diagram out of all of these things. So let's do that just for practice. I see in this alkane 1, 2, 3, 4, 5 carbons here. So I could go 1, 2, 3, 4, and put that one up, and then 5. That would be a very nice line diagram for this alkane right there. We could draw our alkene as a Lewis structure, but that would take a very long time, so I'm not going to do that. For this down here, to do a quick line diagram, I'm going to count 1, 2, 3, 4 carbons. So point number 1 to 2, that's a triple bond. So I'm going to represent it like that. I'm going to make these dots a little bit more visible so that you can tell how I'm representing my carbons. So this would be carbon 1, carbon 2, carbon 3 so far. And then I'm going to bend that line and stick my 4th carbon over there. And if you are paying attention here, you're seeing that there's a little sub 2, which means that there's another one sticking off of there. So again, paying attention to what you are looking at is super, super helpful. Looking at this last one right here, aromatic compounds. Again, I'm not really going to define that or go into it right now, but basically aromatic is a way to refer to compounds that are very, very stable and they have a particular electron orientation. This thing that you're seeing pictured, that little hexagon with double bonds, that is referred to as one of two things, either benzene or a phenyl group. So when it is a part of a larger molecule, we call it a phenyl group. If it's just that fun little hexagon with double bonds in it, we just call it benzene. So if this were sticking off of a much larger alkane, we would call it a phenyl group, but if it's just by itself, again, it's benzene. All right, so that would be one functional group to pay attention to, would be a phenyl group. You can have functional groups that are alkanes, alkenes, and alkynes, and there are a couple of examples of that in the worksheet. You'll see double bonds, single bonds, triple bonds all over the place, and so I'll point some of those out as we go. Other functional groups to pay attention to. This first one down here is called an alkyl halide or a halo group. Again, if our entire molecule is very small and it's just an alkane with a halogen sticking off of it, we would call it an alkyl halide, sorry. And if that particular group is part of a much larger molecule, we would call it a halo group. So there's a little bit of difference in nomenclature there. So we see a couple of examples over here of halo groups or alkyl halides. Here we see that our halogen, our halo group, is this right there. Whereas in the middle molecule, we're seeing a bunch of halogens, right? So this entire molecule would be referred to as an alkyl halide, right? And we're seeing that halo group over here, and that would just be the line Cl. Sometimes you will see functional groups represented like this with this little jagged line. And that really realistically just means that on the other end of this could be any number of things. So we could see this, we could see this. Either way, in both cases, this group is exactly the same. So we would jaggedly cut that here. So you'll see that, and that's what that means. Another way you'll see functional groups represented is this R dash something. So you could see R dash Cl or R dash Br. And that R, think of it as a variable. It's called an R group, and R could stand for pretty much anything. So if we're thinking of our R group in this molecule right here, our R is all of this. The R group in this molecule is all of this. So again, it's a variable. It can be anything. Now, next functional group would be an alcohol or a hydroxyl group specifically. So again, an entire molecule would be an alcohol. If we are talking about a specific group on a larger molecule, we would call it a hydroxyl group. So this here would be a hydroxyl group, that there would be a hydroxyl group, but the entire molecule is an alcohol. All right, so again, we're seeing that R nomenclature, that R group. So in this case, the R is this entire little hexagon here. In this molecule's case, our R is that entire thing. Next up, we have an ether. So if you've ever heard of diethyl ether or any other kind of ether molecule, that's what this is. Basically, two random things bonded on either side of an oxygen. So this is an ether group because we have an oxygen bonded to, in this case, a methyl group and a phenyl group. You can also see an alkoxyl group. You can call it an alkoxyl group as well, because again, we have O bonded to something latched onto something else. But realistically, if you see an O between realistically any two other things, you can call that an ether or an alkoxyl group. Down here, we have an amine. So we have three options for amines. We could have primary, secondary, or tertiary amines. And I am not going to go into what exactly that means, but you can see here, this would be a primary amine, that would be a secondary amine, and that would be a tertiary amine in that order. If an entire molecule is an amine, we can call this little NH2 an amino group. So this would be an amino group right here, as would that. We have thiols here, this R-SH here. We can call that a mercapto group, which is a fancy name. That would be this group right here. We have a sulfide group, so not sulfide as in the sulfide ion. This is a sulfide group or an alkyl group. Sulfide molecule, alkyl group. So SR, again, S bonded to some other things. We can kind of think of sulfide and ether as very similar to one another, except ethers have oxygens and sulfides have sulfurs in them. Down here, we have honestly probably the more common ones that you're going to be dealing with a lot: aldehydes, ketones. This has two C's in it, but there's not supposed to be. This is just carboxylic acid, one C, not two. So again, aldehydes, ketones, carboxylic acids, esters, amides, and nitriles. An aldehyde you will often see represented like this with an R right there. A ketone, again, like this with R's on either side. Carboxylic acids are going to be, again, that similar shape, but on one side you will have an OH and on the other side you will have an R. Esters are going to be similar to carboxylic acids, except you have an OR group on one side instead of an OH. So again, this could be anything. This is an R group, so it could be a lot of things. So this shape, these four shapes that I just drew that look pretty similar to one another, I would love it if you would add that to your notes page just to help you recognize it. Because you'll see these a lot in OChem. Amides are similar to amines, except instead of NH, NH2, blah, 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 you're seeing that oxygen again. So if we could draw this shape over here, we're going to see N on that side. We're going to see O up here, R on this side. And now these could be primary, they could be secondary or tertiary again. So if it's a primary amide, we're going to see NH2 there. If not, if instead it was a secondary, you are going to see N bonded to an H, but also something else. Or last but not least, you could instead see a tertiary one, in which case that R would be replaced, or that H would be replaced with another R group. So really this N is key for recognizing an amide. And then we have our nitrile group, which is really just R, and then you have a carbon, which is triple bonded to a nitrogen. So again, I just threw a ton of information at you. But again, I'm not expecting you to memorize this. I'm not going to test you on it. This is for your information going forward. I do want you to practice it though. So I would like you to pause the video at this point and take a second and try to identify some of the functional groups present in these molecules. There are a ton of functional groups present in these molecules. I don't expect you to identify all of them. Just try to get maybe 2 or 3 per molecule. So hopefully you went through a couple of those and tried it on your own. I will point out a few of these per molecule. I'm not going to go through every single one of them because there's a ton. But our first molecule right here, estradiol or estradiol, I am seeing 2 hydroxyl groups that I just circled, those OH groups, a phenyl group, which is again that little hexagon with all the double bonds in there. For testosterone, I am seeing a ketone group right here with an R and an R there. I'm seeing another hydroxyl group. I'm seeing a double bond here that makes our entire molecule qualified as potentially an alkene. In ampicillin, I'm seeing a phenyl group right here. If we look at this functional group right there, I would call that an amide. I would call this an amide. I would call this one right here a carboxylic acid because of that OOH situation. If we're looking right here, I would call that an alkyl thiol group. Again, that S bonded to 2 other R groups. So those are just the ones that are jumping out at me immediately. There might be a couple more that I'm currently missing. Feel free to investigate yourself. Over down here in the peptide, I'm seeing right away a hydroxyl group. I'm seeing a mercapto group right here, that SH. I am seeing in the middle here an amide, just again right away. I'm seeing another amide over here. In the middle here with caffeine, again, yet another amide. I'm seeing another one over here. I can see an amide over here in our AT base pair. Yeah. Down here in vitamin C, I'm seeing another ketone right there. I'm seeing 1, 2, 3, 4 hydroxyl groups. This one is just a little bit harder to recognize. I'm seeing an O bonded to 2 other things, so we could call that an ether group in the middle. I'm seeing hydroxyl, hydroxyl. There's a ton of hydroxyl groups in this molecule. Over here in ibuprofen, I am seeing a carboxylic acid. I'm seeing a phenyl group there. And then this one down here, isooctane, I'm actually really not seeing any functional groups pop out at me. However, I am noticing that the entire molecule is an alkane, and I know that because there are no double bonds there. We could say that this could be a particular kind of alkane group. They're sticking off on the end. Those specifically are called methyl groups because they are made up of 1 carbon bonded to 3 hydrogens. But again, I didn't really go over the different nomenclature for alkyl groups specifically, so I would not expect you to know that. And I know that I just went through that very, very, very quickly. So if you are confused as to why I was naming those things the way that I am, just realize that much like when I was going over this ketone group, anything bonded that is different can be qualified as an R group. So with a ketone, you have oxygen double bonded to a carbon right here, but anything could be over here. That's why we call it an R group. So in this case, in the testosterone, we're seeing that it's making a cyclic ring, but a ketone could also look like this. That also is a ketone molecule. This would also be a ketone molecule. So again, they can look very, very different, and it takes some practice to realistically recognize all of those groups. So I just want you to try your best. And again, I have the key for the worksheet. So feel free to look at it and don't be discouraged if this is hard for you.